Hello, I'm John Nightingale, a director at JCT and the Symposium host. Now, the 25th JCT Traffic Signal Symposium was an online event this year, and I'm delighted to bring you a recording of one of the presentations. Now, these recordings would not have been possible without the support of a select group of our event partners. So our thanks go to the Institute of Highway Engineers, ITS UK, keepadistance.co.uk, Siemens Mobility, TWM, and of course, our media partner, Highways News. Please check out their short videos, which will tell you about some of the products and services that they can provide. Now, I hope you enjoy this presentation, and we would love to see you in person for our 25th anniversary event in Nottingham Trent University in September 2021. Hope you enjoy it. Thanks.
I'd like to start by saying that I feel really privileged to be invited to give a presentation to the 25th JCT conference, because I believe I gave a presentation at the very first, which I believe was hosted by us at Nottingham University. In those days, I used to give presentations hot off the press of research that we were doing. But today, I'm going to look back over 25, even further into the past, not really just to sort of reminisce, but really to, by way of celebration of what the technology advances have done and how far we've come today. Because I think that's one of the biggest changes that I've seen over the last almost 50 years. I'm then going to take stock and where we are today, and then look at how we can re-engineer and reimagine our futures. So I'll start with isolated control into fixed time signal coordination, introduce demand responsive control, and then how the wealth of data that we get from demand responsive control can be used to manage air quality. And then in the wake of COVID, look at re-engineering cities and reimagining them. And then I'm going to finish with a final comment. Isolated junction design, of course, started when towards the end of the 50s, early 60s, and it was generally because the flows were beginning to increase and people got stuck on the side roads because of the short headways on the main roads. And of course, as road building increased, then of course we had higher speeds, and therefore the gaps were shortened. And therefore it was necessary to start separating conflicting movements in time. Provided arrivals are random, then fixed time isolated junction is still fine today. But of course, we had increase in flow, more signals, and that means that the arrival patterns were no longer random and uniform, but instead they were platooned, and therefore there was a need for signal coordination. Signal coordination simply offsets the start of green, as people know, of consecutive stop lines by the journey time between the two stop lines. Signal coordination, of course, needs a master cycle, and generally we are creating green waves along links and along routes. As pointed out by Webster and Carr, the time distance diagram for a hypothetical coordinated set of signals here clearly shows that unless the geography is right, you certainly can't get the progression in both directions. So generally, we use the green waves for coordinating traffic into a city in the morning and out at night. But as flows increased, we got more signalized junctions, and therefore was a need for a computer model. Dennis Robertson, he created a signal coordination system that actually coordinated traffic over a complete network. It assumes arrival uniform arrivals at the edge, and the data that was needed was traffic flows, all the turning movements and what percentage turning movements, the saturation flows, stop line journey times, and of course these uniform arrivals at the edges of the network were dispersed along the links. And the important thing with the transit was that you had to go out and measure the turning flows, turning movements, using a manual counting. Just for interest, I thought I'd show you some networks here at Newcastle in 1982, and here in Glasgow even earlier in 1978. Transit works by manipulating flow profiles. Here you can see that the flow at each step in a cycle, you've got the green area, which is the, so I've got the in pattern, the traffic arriving in the green, arriving in the red, and of course, the traffic in the red queues up at the traffic lights, and they depart at the beginning of the cycle. The traffic that's arrived in the green prior, while the reds discharge, then has to depart, and oh dear, stop running now. And then, of course, the traffic arrives and departs in the green. And that gives us the out pattern. The go pattern is the maximum amount of traffic that can travel during the green time. The spotted area here is the unused effective green. So the transit model used these in patterns, go patterns, and out patterns to move the traffic from one junction to the next, creating vertical queues. It estimates the delay and then the number of stops and the queue, and together this is a performance measure, and that is minimized across the network, minimizing delay and stops and the measure of queue. Of course, the traffic flows are changing over time, the routes change, and so it renders the signal plan no longer optimal. In other words, the signal plan ages. Area networks age faster than the radial networks, and typically there is a 3% disbenefit of not updating plans. So demand responsive control was introduced in an attempt to resolve the issues of plan changing as well as the aging. An example of responsive control, of course, is Scoot. And I'm going to give some details of how that works. The vehicle crossing over a loop creates an electric pulse, and that is sampled every quarter of a second. And that is the raw occupancy that comes through the 19 message. Now, the model aggregates the occupancies in order to estimate the flow in link profile units or in vehicles per hour. The model assumes that the vehicle travels at a constant speed, arrives at the junction, and it creates a delay. And subsequent vehicles queue up on top of each other at the junction until eventually there is a vehicle undelayed. From this, it can calculate the flow, the delay, the amount of time, the dwell time at the stop line, and the number of stops. Here, 6 vehicles are delayed, so the maximum back of queue is 6. So that creates useful data as a byproduct. In addition, it can assess the back of queue against the distance between the loop and the junction. And if that distance, if that queue gets longer than 50%, then you get a conge value, a measure of congestion. And that's the 4-second number of 4-second intervals that the queue is longer than 50% of the link. Again, wealth of data. Just reflecting, when the first system we were involved with was the Leicester in 1987, and then in 1997, upgrade, more sophisticated, and then in Medway in 2015. So, traffic versus air quality management. More sophistication in the traffic control and management has led to more vehicles on the road and more vehicle kilometres travelled. So it has been increase in recurrent congestion that's lasting longer. As a consequence, we increase the tailpipe emissions and pollution begins to build up in narrow streets. So what can traffic engineers do about this? Well, they can use the data, which is a byproduct of UTMC and ITS, in order to estimate these emissions. So how can we manage air quality? Well, work that we did in Leeds, driving instrumented vehicles around York streets, showed that when traffic's free flowing, of course, the tailpipe emissions are low. All vehicles have to stop at junctions to give priority in the opposing streams. And so therefore you always develop pollution puffs as you stop and then accelerate. If it's congested though, you get a huge increase in congestion. So to reduce pollution emissions, you need to reduce flow and avoid stop-starting as much as possible. Traffic data gives you real estimates of pollution at the time they're being emitted. And this is something that's absent in the air quality grid models that's used by local authorities, because they really ignore the congestion emissions. You take the traffic data from ITS, and knowing what type of cars there are, maybe through ANPR, an understanding of the petrol, diesel, the fuel mix of the fleet, and then the age of the vehicle, which Euro class it belongs to. And this data enables you to take the raw traffic data and create levels, predict levels of pollution. But the pollution is emitted where the traffic is, but that isn't necessarily where the pollution builds up. In order to know where a network the pollution builds up, you need to use the meteorological conditions, and knowing the height and the width of the canyon, you can use modeling to model the circulation of the flow of air and the pollution within the canyon. And the amount of pollution that builds up in any link depends on the orientation of that road with respect to the prevailing wind. You can use the OSPM model to model this in real time using the traffic data and the meteorological conditions. And here it's showing how the pollution can vary as the meteorological conditions change. So by taking your raw traffic data and 5-minute basis, you can estimate the carbon, the pollution emissions, and then using the weather, you can see where it's being spread around the network. If you have that across the whole of the network and produce a map, you can actually build up knowledge about which links in the network, depending on whether you have a northerly or a westerly wind, which ones are vulnerable and which ones are ventilated. That will then enable you to use the signal control, the splits and the offsets, in order to relocate the queues to open space and to cascade queues to spread it around. If you want to reduce carbon dioxide, though, you've got to start reducing the amount of traffic in the network. And to do that, you need to reduce the cycle time and influence modal shift and give priorities to buses and greenways for cyclists and pedestrians. So, trying to now go forward and re-engineer networks, then here, based on some work we did in Leicester many years ago, you use the SCOOT data to find out which links in the network are creating the emissions. And here on the left, you've got a hotspot, and the idea is to change the offset to move that traffic to the open space, and you get the natural ventilation to disperse the pollution. TRL looked at cascading, that was queues, that's shifting the queues, spreading them around along a particular route into the network. But then when this happens, the traffic builds on the side road and traffic can reroute, and it just can displace the pollution. So you have to be mindful of this because you are actually operating the network at a suboptimal, but you're actually spreading the pollution around. So if you have an objective function to manage pollution, then that is a better option. But it's only an important thing to do now to protect people from respiratory problems, etc. But it's only a short-term pollution. So I introduced some years ago this concept of a change in traffic control concept, and this is trying to move away from the traditional minimizing delay to stop, minimizing delay and stops, and just managing people where they want to go from, where they want to go to, when they want to. Also showed that you can actually use signal control to influence drivers' route choice. And I think this is the way forward in trying to use signal control to manage the movements in the network to deliver environmental benefits. So I introduced this concept of environment capacity, where traditional speed flow curve showing the traffic capacity, we really need to start reducing flows and speeds to get the traffic moving more smoothly, to give you to achieve an environment capacity, or even further reduce flows and speeds to deliver your carbon capacity. To do this, we can capitalize on data and have to start asking questions like, what is causing my elevated pollution in this link? Is it the cars, the taxis, the buses, pedestrians, cyclists? At what level of flow and speed and duration of congestion can we have and maintain on this link in order to meet the air quality limits? At what level of flow will I deliver the carbon target? COVID has presented us with an opportunity, perhaps. Bus occupancies have reduced due to social distancing, and there's more cycling, but what will happen in the winter? People are working from home, and we have mode shift to more use of cars, even though there are fewer people going into work. And there is a pressure on car parking spaces, and there is very little secure and safe parking for cyclists. So let's think about reimagining our networks. We asked the question, can network control and management and ITS reimagine networks to support economic growth by putting the environmental objectives first? The requirements would be to facilitate mode shift to sustainable transport and to develop the idea of pedestrian and cycle focused performance measures. The emphasis is on seamless door-to-door services, which are a real alternative for cars. We'll be needing to integrate transport systems, introducing shared mobility to provide that first mile, last mile, and the local trip and travel for local trips. We need to facilitate the collaboration of bus operators, perhaps with teachers and parents, with with businesses, to start matching services to the needs of the public. But ultimately, we really need to reduce the need to travel. So the idea would be to create a vision for the future and develop a roadmap which will give us incremental steps to achieve that vision. So, some ideas. Reduce the demand for travel. Well, were people working at home? That's reducing demand to travel. But if we stay at home and use the heating, then we're 70% more likely to, we will emit 70% more emissions than we save by not going into work. So maybe we should have local hot desking facilities. That will also get over the issue of isolation. The cities are changing. There's less shopping. There's fewer shops closing because of people are not in their business premises. So in the future, we probably will expect some real estate becoming vacant, which maybe should be converted to housing. So perhaps moving to company mortgages instead of company cars. The business practices will possibly change to get out of phase working. So can we alter these working practice to maintain lower levels of traffic in the cities, and then we would need fewer car parks. Local authorities of the commercial sector can work together to provide the secure parking for cycling that's needed, and maybe showers. And of course, in the future, networks will change so that we'll need more space, physical space for pedestrians to accommodate queues and bus stops and people queuing at bus stops. We need to get a shift to public transport, and to start with, we need to reinstate public's confidence in travelling by bus. Maybe travel cards aligned with the new changes in work practice, only going into work 2 or 3 days a week. Bus stops can act as catalysts to create hubs to integrate with cycling and shared mobility, and to facilitate door-to-door services. Bicycles could be carried by the public transport itself. Maybe public transport also doubling up as delivering parcels, and perhaps redistribute bikes on bike hire schemes. Operators working with schools so that taking the bus to school becomes the norm for all children. And then trying to get bus businesses to work with public transport to map their new their new business practices and to use the bus services, but outside the school run. And then, of course, retail, looking at how they can be opening hours can complement other demands that the other demands in the bus services will claim. So what's the implications for UTMC and ITS? Well, this wealth of data, we've got loads of know-how, we've done research, we have the expertise to start thinking outside the box and reimagine these futures. We can study the existing data to understand the problem, and of course we can learn from the COVID experience. We can begin to identify the thresholds for the traffic characteristics to deliver the air quality and carbon objectives. We can use the canyon model with meteorological conditions for a dirty year and a clean year, and then we can explore how sensitive our network is to the weather, and use 12 months of data to test, well, what happens if we have introduce clean buses or electric vehicles. Another issue is how do we evaluate the changes and how well we are performing. And that can be done by taking the data from the system so we can continually monitor changes from day to day. By introducing small changes in splits, offsets and cycle times over a longer period, then we can actually reach environment capacities. And I would advocate that the drivers will not notice. It's shocks in the system they don't like. But at the end of the day, we really need to start looking at the need to reduce the amount of travel. So data gathering with the UTMC, routine data capture, real-time processing, synchronizing, 5 minutes, diagnosing problems, and understanding the problem and designing solutions. Suggest you be clever with the emission-sensitive performance measures to weight specific links and constrain the signal settings to deliver these environmental benefits. Be proactive and gradually give more capacity to pedestrians, cyclists, and take it away from the traffic. And then what we'll be doing is switching to a people-focused performance measure. But if we do that for buses, we need to know the bus passenger counts. So how do we achieve that? How do we manage the interaction of the different sustainable modes as the flows of these sustainable modes increase? And how do we manage pedestrian and cycle congestion, which we could anticipate will occur in the future? Emphasis may then need to be on the safety of movements of people, how we enforce cycle paths, etc. How do we facilitate the access and the egress of these sustainable modes at interchange hubs? So how will things change in the future? I'll finish with a final comment, because I'm not trying to put the world to rights here. What I've tried to do is to sort of set the scene for a paradigm shift in the way we actually approach the signal design of networks in the future. And it's really a matter of trying to set down some ideas that I've had and how we can re-engineer the management of control in the future, and re-engineer it and reimagine it. What will it look like in the future, and how can we plan? But simply what I've tried to do is give you some food for thought, just to make sure that you reflect and try and make a difference. Because my generation has created the problems, it's up to you lot to solve them. Thank you for listening, and any questions?